All right, so for today, I'm going to divide that into two halves. The first half, we'll do some theoretical analysis about doubling strategy for dynamic arrays. And then hopefully we'll take no more than 35 minutes. And then we'll take a break, and then we'll do some Java programming. But the solution for Java is already there. It's really for me to go over with you, just get, back to the Java mode, right? We'll take it slowly, gently, okay? For materials, you guys know where to find, but just a quick reminder, right? You will see for today is tutorial number 3, okay? So for the second half, you're going to need a Java starter, right? You can feel free to download it and also to import it, yeah? You know how to do that. And then I'm going to use, for the first half, you can look at the instruction as well, but I assume you can read it either before or maybe later. And of course, I'm going to use this blank page over here to go over dynamic array, doubling strategy. Okay, I'll start with that. Okay, alrighty. Okay. So the way we're going to analyze the second strategy here for dynamic array, which means you don't really have a fixed size of the array all the time. You can grow it. Right? So there are two ways for you to grow the array. Either you can say every time I want to grow the array, I only grow by size maybe 10, only one extra 10 slots. Or I can say if I currently got 10 slots already occupied, I'm going to double the size of the array, right? Keep doubling. So we're going to see that it's very interesting that this, just by modifying only one part of the code, is actually going to make it, average case-wise, much more efficient. That's something we'll see today. Okay, let's go over the code very quickly, but it's mostly identical to the the constant increment strategy. Okay, so we basically got over here, we got some array, and then we're implementing a stack. Of course, if you want to implement a queue, so it'll be very similar analysis. Okay, so let's say here we got some initial size. Okay, this is important, right? Just to make sure, oh, sorry, too thick. Right here, right? This I. And the capacity here is going to denote about the current number of elements that's already in the array, right? You will see. Okay, we just got different symbols over here, and then the way we're going to do the math, we'll just reuse the programming variables. And then we got some array over here, okay? And over here, we're simply just trying to initialize the I to be something, right? So here, the actual initial value for I doesn't really matter. So in the mathematical analysis, we'll just say I, okay? And then the capacity initially will just be I, but capacity might grow. It could be, for example, I, 2I, 4I, etc. Okay? I will just write it down right here, but you will see another place. Capacity here initially will be I. And then let's say all the I elements are filled out. In that case, we're going to grow the size of the array by 2 times. In that way, it's going to become an array of 2I elements. And then the next time, doubling again, is going to be 4I. And then, etc. Of course, we're going to modify. So we're going to observe the pattern there and then to make some generalization. That's something we'll do. All right? Let's move on. And of course, this is just some Java-specific details. So up to this level, I will expect you guys to maybe take a look at that and then try to play with it. All right? So that one we wouldn't spend too much time. And we're talking about the push operations right here. All right? We're going to analyze about how efficient the push operation will be. All right? But it's very important to emphasize, back in the constant increments strategy, we distinguish between worst case running time versus average case running time. So they're different. All right, so we're going to make the similar distinction as well right here. Okay, let me go over the code, and then I'll tell you what I mean. So this line here is really important. Okay, this line here. This line here is the condition where it's going to trigger resizing. So this one here is going to trigger resizing. Okay, let's highlight it and try to understand what it is saying. If the current size, meaning that the number of elements that's already stored in the array, reaches the maximum size or maximum length of the array already, in that case, we should really resize the array. Otherwise, we might run into array index out of bound exception. Okay? And then this part over here is mostly identical to what you learned earlier about the constant increment, this part here, right? So this part here, if you kind of recall, we basically have to create a new array with certain new size, right? I'll get to it in a moment. You got to create a larger array, and then you got to copy over the old contents into the array. And then you're just going to assign one by one, and then eventually you're going to make sure the array references are reassigned as well. Let's just visualize very quickly, right? It doesn't hurt to really have some recap also from before. Of course, the only change is we now say capacity multiplied by 2. Before, let's say for constant increment, it would have been, for example, versus if I say capacity plus some constant C, right? So that will be just the other strategy. Just by modifying this line here, just this expression, it's going to make it so much different, right? So that's something we want to see. We can only see that precisely by applying math. That's something we'll do, okay? And think about what's happening here. What we're saying is, currently your array is like over here. So we have data. And the data currently is completely filled out. And the size of the data is simply capacity, right? The length, right? Capacity cap, right? Over here, okay? The doubling strategy is saying we're going to reassign data to some larger array. So the way to do that is we have some temporary array. So we're going to create a temporary array that's going to be just double the size. Right here, okay? So you can think about double the size. This part here is capacity, and this one here is capacity. Of course, capacity might be different value, you know, depending on where you are in the resizing, right? And then, of course, this part here has to be copied over. So this is really the dominating part for the algorithm, because if you go from here to here, you have to run a loop to really copy everything over, right? So that one there is really the big O of n that we have, right? And of course, you can think about this part here. I'm going to put in green. So green here simply means there's a free space, okay? So this will be the temporary array. And then eventually, we're going to say data will just be pointing to the temp, okay, eventually. All right, like that. Right? It's like an individual step, but we have to see how exactly it's going to go average-wise. We're going to amortize somehow what's happening here. So now let's think about for this particular push operation. And after that, you just got to update, right? So certain parts, since we're pushing things, okay? So now if we try to look at the worst case running time, right? If you look at the push, so there are two possibilities for the push. Either the push is going to trigger some resizing. In that case, we're going to execute the orange block, which will take big O of n. But if we didn't have to do resizing, we only have to execute these two lines, meaning that we only have to execute these two lines, meaning that this if condition is false. And this will be big O of 1. But what's the worst case? Big O of n, right? Not big O of 1. You cannot assume you always got a best case. All right, so that's really important to clarify. Big O of n will be worst case. All right, just based on the code right here. If you're only analyzing this block of code in isolation, big O of n, you can do it already from 2101. But now we're going to do something a little bit more advanced. We're going to consider what if you got a sequence of pushes altogether. Maybe things wouldn't be so bad as you might think, right? That's something we're going to do, okay? So this is something called amortized analysis right here. So when we say amortized analysis, it's more like a calculating average, which will be we are going to get the total running time over n pushes. Once we got a total running time, we're going to say divided by, you can think about the number of operations. In this case, it will just be n. Okay, so that's the big picture, what we're doing. And it's also very important to talk about this assumption here. Okay, let's talk about it quickly. Okay, because we kind of did similar kind of assumption there for constant increment. We're going to do the same thing. Okay, so what we do is we assume that we got n pushes, n push operation. And we assume that the very last push operation triggers the last resizing routine. Okay, so that's something I kind of explained in the constant increment, but I can do it again, just to make sure you're fine. Let's now try to visualize what's happening here. What do I really mean? The very last push, right? Every push is going to add the capacity by 1, right? If you got n pushes, how many elements would you have already got in a stack? N elements, right? Let's understand that, okay? Let me visualize this one here right away. It's going to help a lot. So what we're saying is, after n pushes, we have an array that looks like this, roughly speaking. N elements would have been already occupying the first n slots. So this here, size is simply just n, okay? I know it's a little bit small. Okay, I'll make it a little bit bigger, just for you to see. Right, think about n. So guys, this one here is so important, all right? This is so important. It makes sense, right? After n pushes, you got n element. We don't delete. We don't do any pop, okay? And what about the rest? The rest over here is just going to be some free spaces. How many? We'll see. Just to get an intuition, you don't need to know exactly how many. There will be some free slot. This will be the free space created by the last resizing. All right. Any questions so far? All right. So if your so far is good, that's, I would say, about 50% is done. Okay. So now let's try to observe some pattern. Okay. Let's take a look at the pattern here. Let's say we got our initial array, and we create it pretty much here. Right? Capacity is simply equal to I. So that means initially we got all the I slots available for us initially. Okay, so green means it's empty for us to store something there, and pink is going to be something that's already occupied from left to right, right? Just doing pushes only. Okay, let's say talk about the first resizing. What does the first resizing really mean? It simply means the I empty slot we have created have all been occupied, right? So that means this part here really corresponds to this part here. There will be I pushes already. And after the resizing, because we have to create an array of size 2 of the current capacity. So what used to be of length I is now going to be double the length, 2 I's. All right? So think about this. So that means this first I slots is already occupied. We created I slots in the beginning, and then at some point, all the I slots are occupied. And then we execute this block here to shift to really copy everything over in a bigger array. And the bigger array makes sure we got another I slots free, so we can do more pushes before the next resizing. Okay. Okay, I'll pause for one moment. Is there any question up to this point about what the first resizing is supposed to do? You only do resizing when the current array is completely filled out, of course. Right? All right, after this, we can think about what's really the cost for the first resizing. Okay? And then we're going to figure out the cost. Okay, I'll put the cost right here. So after the first resizing, we have to make sure we copy everything into here, right? It's going to be exactly I, right? You can think about that for loop over here is going to run exactly I times. Agree? Okay. It's going to be exactly I. All right, let's do a few more, one or two more. Let's say we now live with this array, which means we can do another I pushes, right? Let's say after, okay, let me put something here very quickly, right? That can also help. When we go from here to here, is actually after I pushes. And this one here is actually after another I pushes, right? which means what we have is we got 2i elements occupied. If the 2i element occupied, so now the array is full. What should we do? Well, it's going to trigger another resizing. The resizing is actually going to create another array, capacity times 2. Capacity used to be 2i, is now going to be 4i. And the first 2i elements are simply copied over from before. So that's the cost. All right. So that will be the 2i right here. Okay, so this one here will be 2i. 2 times I. Any question about it? All good? Okay. Let's, even though it's not really here, why don't we sketch a little bit? What about a third resizing? Okay, anybody kind of apply the same principle? What's going to happen? What's going to trigger the third resizing? And what's going to happen? And what's the cost? I'll pause right now, because if you guys don't really follow this, it's going to, the math wouldn't make, would be useless, right? Third resizing, yes. What will be the triggering condition?
If all 4 were occupied.
Okay, I'll pause there, please. So what you're saying is, in the third resizing, is all these 4, of course, all these 2 will be already filled out. So that means this this array of size 4i is completely filled out. And then?
And then the cost will be 4i.
The cost will be 4i.
Right.
What will be the cost?
4i.
4i, because you got to copy all the 4i elements into the new array, right? Okay, good. Why don't I put it here very quickly? Okay. So the third resizing is going to be roughly like this. Again, it's going to be all the 4i elements are occupied right here. And then when you actually try to create a new one, it's going to be 8i. Keep going, right? So think about here, it's going to be 4i. 4 times I. And this part here is also 4 times I. The cost is really about copying all these elements into the new array, right? So the cost over here is 4 times I. All right, so have you, somehow there's a pattern here, right? Maybe. Let's take a look. Okay, we can already observe something. Yeah, as I kind of mentioned briefly in the lecture, whenever you see, okay, you can see here, we got some multiplicative constant. We got something here. And we got something, it's not explicit multiplicative constant, but we can write it out if we want to, right? So you can see that this one here is really 2 to the power of 1, right? And this one here, 4 over there, is really 2 to the power of 2. Right? This one here is 2 to the power of 0. So now we can kind of see a pattern there, right? Depending on which step you are, somehow the exponent there will have some correspondence, somehow. Okay. Now, if we actually got 2i, I, 2i, and 4i. Now, it seems to be a pattern, but now we learn about 2 patterns. Is it arithmetic sequence or geometric sequence? Geometric, okay. If you say it's geometric sequence, this will be the first term, I agree. What will be the common factor?
2 to the n minus 1.
Common factor.
Oh.
Common factor simply means when I go from this term to this term, there's a common factor. When I go from this term to this term, there's another common factor, right? Would you agree too? Yes, agree? Because you can see that the exponent here go from 0 to 1, and then 1 to 2. And that is the base is 2. So that means we got 2 multiplied by 2, and then multiplied by 2, right, every time. Okay, a question?
Why would I not be the common factor?
The I here? Okay, good question. What we are really saying here is this. So here we are saying 2 to the 0 multiplied by I, and then 2 to the 1 multiplied by I, and then 2 to the 2 multiplied by I. You want to think about, if you want to calculate a common factor, right? Think about you're trying to divide this over this. I'll show you. So this will be 2I, and then divided by I, you just get 2. That's a common factor. And if you divide this one here over this one here, it's like a 4I divided by 2I. And cancel out, you also got 2, right? That's a common factor, right? Good. All right. We'll kind of see a pattern, but not just complete just yet, because in order for geometric sequence to be sum using our formula, we want to know how many resizing exactly do we want to do. That's a problem, right? I can tell you it's not n. We say n pushes, right? But if you say n resizing, that means for every push, you're going to trigger some resizing. Not really, right? So now we're going to figure out. That's the trickiest part for this math here. But I'll lead you, okay? Let's now look at the last resizing, okay? After the last resizing, we're going to get somehow an array, somehow, right? Just arrays like this. And according to our pattern, after every resizing, we can divide the array into 2. The first half will be completely filled out. And the second part will be the new spaces we're creating, right? So we say after the last resizing, that should be the pattern. So what we should have is something like this. We're going to get this part over here occupied, and then about half, exactly half. And this part over here will be free slot. Okay, so that's a pattern. Okay, having this. Let's now, it's not exactly precise yet because we still don't know exactly what's the cost for the last resizing, right? You can see we got things like this one here, this one here, this one here. But what should be the exponent right here for multiplied by I, right? We haven't really figured out that yet. Okay, I would suggest let's write out a sequence, just as a sketch, and then we'll see. Okay, let's try that. So what we want to figure out is the total running time. So we have the total running time. Okay, it's going to be starting from 2 to the 0 times I, first resizing, plus 2 to the 1 multiplied by I. That's the second resizing, plus 2 to the 2 multiplied by I, and then all the way to something. Okay, I'll leave it just for now. Okay, we'll go slowly here. This guy here is the first resizing, which corresponds to right here, right? Copying this. And this one here corresponds to the second resizing, which is about copying everything into right here, right? And this will be the third resizing. How about the last resizing? How many elements will we have already copied by using that loop? I would suggest for this one here, look at the assumption. I already drew some diagram for you. Tian? Just n, not n minus 1. Because after n pushes, you got exactly n elements, right? Just n. Okay, good. All right, so I want you to refer you back to this assumption here. So we are saying that after n pushes, we got exactly n elements right here. So those n elements will be the ones we would have already copied from this for loop in the last resizing. So when you actually study for this example here, the most important connection points is to really visualize this assumption over here. And then when you see the pattern for the last resizing, this part over here really is just n. Okay? So this part over here is really n. You may have so many i's over there, but just n, after n pushes. After n push operations, right? Pushes. Okay, so let me put n here. And we are still not there yet. Recall the formula. I'll put it here. Remember we derived the formula for geometric sequence sum. Okay, I'll put it here. Okay, let's see what's missing. So we have the sum of geometric sequence. So that one there. Okay, I'll put it down here. You can double check later. Sk, where k will be the number of terms, right, in the sequence, but we don't know yet how many terms are there in this sequence. But we'll work out, right, just k. And then it's going to be initial term, I. I somehow just happened to be the very first term I. I kind of chose that deliberately, right, just I in this case, okay? And then that will be r to the power of k minus 1 divided by r minus 1. In this case, we know that r is simply just 2, right? Because doubling, right? But now the question is, what's k? That's a question. Right? That's missing. Okay, so you can see where we are now. So let's say this. Let's say this is the kth resizing. All right. And if that's the kth resizing, we have to see the pattern right now. Okay. If that's a kth resizing, what should that be in terms of the pattern here? K minus 1, I agree. You're definitely on the right track. But I want to say, I know this is the kth term, right? Can you rewrite it rather than n? N is definitely right. It's just one way to think about it. Can we rewrite this term here in terms of something like this? Like the common factor to the power of something and then multiply by I. 2 to the power of k minus 1 multiplied by I. Okay? K minus 1. Yes, exactly. Yeah, you're right. All right. Okay, I'll write it down and then I can pause just to see if you guys got any question. So this n here at the same time will also be 2 to the power of k minus 1 multiplied by I. Okay? Here's the reason. Okay? We know that we got exactly k terms and the exponent will be 0, 1, all the way to something that will make it k terms, k minus 1, right? So that's why your fellow student said exactly, that's just k minus 1, right here. Okay, now we're getting to somewhere very promising, because now what we have is, we actually got n here, also we got this term over here. They should be equal value. All right, let's now do a little bit solving the equation. Okay, let's solve it, okay? Let's try that. Okay, I'll solve it aside. Okay, right here. Okay, so we know that 2 to the k minus 1 multiplied by I equals n. And we want to know what k is. Once we know what k is, we can substitute that value for here in the formula. And then all the rest, it will be simplification. Okay? How do we solve it? How can you somehow solve the k in terms of n in this case? Looks like, actually we did something very similar yesterday. Remember when we were trying to bound the number of we are trying to bound the value of h, like a height of the tree, using the number of nodes in the tree. We kind of use the log, right? Well, we can use it something like that over here. All right, so log will also be your friend, right, for this course. Okay, okay, let's take a look. Okay, okay, I'm just gonna write some property here, also for your reference as well. Okay, okay, so this part, okay, we don't need it anymore. Okay, so property number 1. Okay, we know that. Just a reminder, just about what's the definition for log. If you say 2 to the x equals y, that would simply mean x here, the exponents, will just be log base 2 and then y. Right? So when we have a log without an explicit base, it's simply 2. All right, one example right away. Okay. We know that 2 to the 3 is equal to 8. So that means log base 2, 8, would just be 3. Okay? Okay, so that one, property and example. Okay, so now let's try to solve this thing here. So what we have is, let's now, before we take the log, because you can, so let's see what this is. This should be exactly n divided by I, right? So we know that 2 to the power of k minus 1 equals n divided by I. And then we can now take the log from both sides. So that means we got the log. What will be the log of 2 to the k minus 1? Do you know that? Okay, I'll put it here. Yeah. First of all, I'll write it down here. So we take log here. Log 2 to the k minus 1, right? Which will be, by definition, if you look at the property here, it simply means 2 to the power of this particular power, and then take log, would just be k minus 1. Right? That would be k minus 1, and that one is exactly equal to the log of n minus n divided by I. So what we get is right here. Okay. Now let's now move things around. We're almost done for this most critical part. K will just be the log n divided by I, if you like. Let's put parentheses and then plus 1. Right? Minus 1 and then plus 1. Okay, so this will be the ultimate answer we need. Right here. Yeah, for the math part, maybe you want to maybe do it yourself as well, just to make sure you feel comfortable. If you get a big picture, that's a good sign for today, right? I know it's complicated, right? All right, let's now write down the formula. So now we know that the k here, right here, is exactly this. Okay. So what we can do is, let's now continue with this. The total running time is going to be, okay, so I times, okay, the r to the k. R is 2. 2 to the power of k, which will be this whole thing right here. Okay. This whole thing will be the log n divided by I, and then plus 1. Okay, just like that. And then minus 1 divided by 2 minus 1. Right? Just remember the r that we're talking about, since it's doubling, so it's just simply 2. R here and R here. Okay? But now, how do we simplify this guy over here? Okay? Okay? Let me remind you another property here, another 2, and then we should be able to do it. Okay, property 2. So property 2 over here. That one is very basic. If I got x to the power of y plus z, it would be just x to the power of y products x to the power of z. Basic. Okay? Because right here you can see that 2 to the power of this plus this, it would be 2 to the power of 1 multiplied 2 to the power of this. All right? That's why I'm using it. Okay? Another property, very quickly, will be right here. So property 3. If I have 2 to the power of log x, base 2, of course, what would that be? X, yeah, exactly. Yeah, that's right. You can plug in some number, right? It's definitely not rocket science, right? Okay, so this will be just x. All right, so with all these properties, that it's also nice to review them at the same time. Okay, so what we have is like this. So this part over here is just going to be right here. Okay, I'll put star star. The star star over here is just going to be 2 times n divided by I. Okay, you can work out that particular part of the math. Okay. So what we have over here is we got this part here is simply just 1. 2 minus 1 is 1. So it's going to be I times n divided by I multiplied by 2. And then don't forget this minus 1 here. Don't forget. All right. Minus 1. Okay, let's simplify. We're almost there. Just 1 minute. Okay, this one here. If you distribute I over that, it's going to be 2n minus I. And we know that I is just some initial capacity. So that one is a constant. So it's not going to impact asymptotically. So this means big O of n. And you might be wondering, isn't that the same as the worst case? Right? You can see we have done all these kind of mathematical work. Big O of n is the same as big O of n. Is there anything wrong with what I just said? Let me say that again. It seems like after all the math equation here, all the summation, we got big O of n, but that one turns out to be just the same as the worst case running time. Can I just say that for doubling strategy, worst case and average case, they are equally bad? Yeah, challenge me. Tian Tian, go ahead. Exactly. So the reason we are doing this geometric sequence here is about over n pushes. So here is total running time. You got to divide it further by n. Don't miss that last step. All right? All right. So the amortized case is going to be the big O of n divided by n pushes, which will be big O of 1. So it's definitely a very efficient strategy. So task number 2 for your tutorial asks you to compare the worst case versus average case between these two strategies. So that's something I will let you do it. You also see some information on the slide as well. But this derivation process here is something very important. You might be given something similar. Okay? So the best way to really understand, to kind of be able to do something similar would be, of course, understand this one first and make sure you can do things from scratch. All right? Any questions before we take a break? Okay. Okay, I'm going to leave you guys to that, right? You got everything available to you. Okay? Why don't we take a break and we take attendance? How about that? Okay, second part for today. Let's switch to Java a bit, right? Rather than theory. Okay. So you can download the starter from the lecture site. You will see that it's right here. Okay, I'll let you download it and import it. I'll import it right now. I just downloaded it myself. So it's already on my desktop right here. And so there are 2 tasks over there. We'll go over there. Let me just import first, right? Import project, existing project under general. Next. And then you gotta browse to where you store the zip file. Let's say desktop, and open it, and finish. Okay. And it is expected not to compile because it gave you the JUnit test cases, but you actually didn't have any code, just supply. That's intentional. So your job is actually to figure out the classes and methods to really declare and then implement them to pass all the test cases, right? So that will be the pattern you have to get used to for also programming test later. Okay, you got 2 programming tests to test on this pattern. And I will also try to set up your assignments in the identical way so you get used to it too. Okay. Right, let's now go over something here. Okay, of course, it may not be every detail. I'll try to go over all the critical part. I want to do some visualization as well, just to show to you how you can understand this code here. You will see there are 2 classes over here. One is called BST node. You can think about the BST node. It's a little bit like a link node, right? It's a link structure that we're trying to implement the binary search tree. So every node, I'm going to go over the structure for this class actually separately because that's important. You're going to use it also for later assignments and also for programming tests, at least programming test 1. Okay, I'll go over that in just one moment. But I can assume that this is going to be more or less the structure you will be given in your programming task. And then this second class here under the tests package is right here. Oh, let me make it bigger. Okay, for now, you only got 2 test cases, right? You got one here. That one just kind of showed to you how you can, I'll talk about it. So you got, you can create different nodes in isolation, and then you can try to set the links between them, left and right, and also the parents. And then you're trying to call some method, right? So we are going to create a class called BST utilities, right? So in Java, if you don't have the class just yet, it's going to complain that it's unknown type, right? That's kind of basic, you learned back in 2030. The first method that we want to implement is just for in-order traversal, right? We kind of did it in the lecture. We're going to see very quickly how you can do things recursively. That's a good recall, also from 2101. Okay, we'll get there. And the second one there, which I may not just go over the Java solution. That one is very, very standard. Just doing binaries, basically doing a search over a binary search tree. Just either go to the left or go to right. Right? That one there you can just look at the solution. And I will really encourage you to really look at how the JUnit test cases is really trying to tell you what the requirement is about. Because when you're given something like this in the assignment or in the test, you are the only one to figure out exactly what's required. Okay, just get used to it. Okay. Okay. Before I start coding, let's now look at something very quickly. First of all, let me start with this BST node class right here. Okay, quickly. Okay. So there's a BST node, and you can see that first of all, this class over here is generic. Right. This one tells you that it's a generic class, meaning that when you are trying to use this class, you can pass any type, like a string, integer, person, etc. Right? That's kind of generic you learned in the previous course, right? Also, generic is very important when you program graph later. We also got to make it generic. It's the way to go whenever you try to program collections. Okay, so there are 2 attributes here. So you got key and also actually more than 2 attributes. You got key and also you got value, and also you got parents. You got left, and also you got right. All right. So these are the attributes you can expect for each node. I think I might have a diagram right here. Just give me one moment. Let me just copy that. Yeah, there we go. Let me copy that and I'll explain quickly. Oh, sorry. There we go. Copy. Okay. So every time you're creating a node, okay, like that. Okay, you can think about the key over here is going to be for searching purpose, right? The key over here, we just assume is integer key, right? Just integer, can be any value. Okay, the value here just the data. Okay, it can be string, can be person, whatever value e here is going to correspond to how you instantiate the BST node. For example, you might say BST node string. In that case, every occurrence of E inside this class is going to be replaced by string specifically, right? If you instantiate E by different type, it's going to create differently, okay? That's something just want to review, okay? And then you got key, you got value, and also you got left and right. So these are simply, that's how we make the tree structure recursive, okay? So you basically got left child, right? It's going to point to another node right here, BST node. Also, you got right over here. It's also going to point to another BST node, right? You can go on and on and on. However, it is very important for you to distinguish between external and internal nodes, okay? A very good practice is really design something called sentinel nodes. Okay, I'll show you another diagram, which you will see on the slides as well, okay, right here. So here, let's say we're only showing the key value right here, right? So this is a binary search tree, just a binary tree or binary search tree. Any nodes that actually store meaningful key values, we call them the internal nodes right here, okay? So the green ones are the internal nodes, storing some meaningful key value. Meaningful in the sense that the value can be compared against if you want to do some searching or you want to insert something. Okay? On the other hand, the bottom level there, we consider these the external nodes. For example, right here, the square. Okay? So these are the external nodes. They might still have some default value, for example, like a key 0, or can make it -1, right? Just some default value there. They are not really meant to be for searching. They are more like a placeholder, which you will see. Okay? The key is not meant for searching. Not meant for searching. Okay? We got internal, we got external, right here. Okay, just to see the difference. But now how do we distinguish between them in Java? Okay, just the convention you can see in the test right here. You got two constructors. You got BST node, where you don't pass any inputs, no key, no value. So that you call this constructor here for creating external nodes, in which case the key and value will just be set to some certain default value. Okay. Let me see the BST node here in Eclipse. I can double check for you quickly. There we go. You can see that the BST node, I can see this is the one without any parameter. We simply, the code you're given, set everything explicitly to be null, and the key value there will just be -1. Okay, just to say it's an invalid key value for external node. Okay. Okay, so this one here is really for creating external node. Sorry. Okay. So this one here is really for creating external nodes. External node. Whereas this one here with parameter, key, and value. So that one there is for us to create internal nodes, right? So that one there is for creating internal nodes. Internal node. And then we got different methods there, right? You can easily check to see whether the node is actually external or external simply defined as if the left child and also right child is simply null, right? You can think about here the diagram. This will be external because there's no further branching. It's simply left and right will just be null. So these are considered external nodes. On the other hand, the green one here, you can see left and right, they are simply external nodes. They exist, but just not null. Right? So these two methods, you also want to pay attention to them. Okay, it's external and also is internal, right here. Okay, and then the rest will just be some very standard, setters and getters, that you can use. Right? You don't need to redefine them. You'll be given. Okay, you just got to be very familiar with all the code that's here. Very simple self-contained class. So when you're trying to program any algorithm on the binary search tree, these should be sufficient. If you need some extra, like a helper method, I will let you know explicitly, right? But this will be a good one to start with. Good. Any question about the node? All right. And I want to definitely program together with you about in-order traversal. That's something you know pretty well. Good to get back to the recursion pattern you learned from 2101. Before I get there, I want to talk about very quickly the test case. Okay, very quickly. Okay. So this one here, you can see that what we're doing is, let's see what we're doing. I think that one there, I can simply copy this, right? Give me one moment. You're going to save some time. One moment. There we go. Okay. Here. I'll make it a little bit smaller right here. Okay. Let's say on the right-hand side, this is the tree that we actually want to create using the BST node class that I just talked about, let's say, right? The way to do it is you want to create all the nodes in isolation. There are different ways you can actually try, right? You can maybe try to create the nodes and set the parent and child references along the way. I personally like to create all the nodes in isolation and then set the links in a different block, right? It's completely up to you, right? Let's see. So we got 3 internal nodes. We got N28, N21, N35, right? That would be Alan, Mark, and Tom, all right? So basically what that would do is N28 is this node. And then N21 is right here. And also N35 is here. So far, there's no link between them just yet, but imagine there's no link, okay? And then we got 4 external nodes. We want to make the tree complete, right? It's a placeholder, okay? So we got external 1, 2, 3, 4, okay? So what we do is we're going to have external 1, 2, 3, and 4, okay? It turns out this will be external 1, and this will be external 2, this will be external 3, and this will be external 4 right here. Okay, so these are the 4 nodes. But let's see how we can set a link. I'll show you one example, but you can trace the rest. For example, you can see that right here, when we say N28 is set left, N21. So that means I want to set the left of this node here, N28. The left should be N21, right? So I'm basically saying the left of that should be set. Okay? That one is really setting this. All right? Follow? Okay? So of course, you got to set also symmetric link. For example, you will see that symmetrically, N21 will set its parent to be N28. So you can think about symmetrically, you will also say to here, it will be also the parent's reference as well. Okay? So I'll let you guys maybe convince yourself all the setter methods call is going to set up this tree over here, right? I'll let you do that. It's going to be tedious to do everything here. And then let's now take a look at this block over here, given that particular tree. So what we're doing is right here. What we're doing is we're trying to use the tree and then try to make sure that in order traversal starting from the root. In order traversal starting from, this will be the root of the tree you want to start with, right? So we are starting from this particular one. And we know pretty well it's going to be 21, 28, and 35, right? Okay, that's exactly what these assertions are showing to us, okay? I'm going to leave you guys to make sure you understand about why the assert equals assert true is really asserting. We got only 3 elements in the in-order traversal, which will be 21, 28, and 35. And that is exactly in that order, okay? Okay, so the exercise is to read this JUnit's assertions and understand. Okay, that'll be a nice exercise for you to know what's going on. So this one documents about what you should really achieve by the in-order traversal. Let's now program that, right? Let's do that together. The solution actually is a little bit, the solution, I just kind of changed that, just a few minutes before I came to the tutorial today. So I think this one will be a little bit better, maybe more corresponding to the pattern you learned, maybe back in 2101. But let's go over this. I think it's a very general pattern for you to look into. I'll get to it, but I will just program first, okay? So from this one here, first of all, we are missing the BST utilities class. We're missing it, right? So what we should do is now right-click in the model. So everything should go to the model package, right? That's something I'll put as a requirement as well for the assignments and for the programming test. Just gonna make sure everything that should be graded should go to the model package. So I'm gonna say right here, BST utilities. You can see one thing here that's also very important. You can see BST utilities, we are not instantiating it into string. right? It's a particular instantiation of the generic parameter. But when you define that class specifically, it has to be generic. You cannot just put string, right? Okay, so you got two choices. Either you can put angle brackets E over here, or you can add it, after the class is created. Doesn't matter. Okay, I'll just add it now already. Finish, all good. Okay, so that's our BST utility class. You will see that at least the compilation error right here go away. Right? So this part is okay. However, it's showing that we don't have that particular method, right? So you will see that there are two compilation errors right now. One is about in-order traversal. The other one is about the search. Okay, so that's kind of very basic. So I'll let you guys to really see that if you are able to work out what method should be created. But I'll go directly to the solution. Okay, BST utilities right here. Okay, so there will be two methods we have to create. Okay, the first one is something I want to go in detail. Public, okay, and then array list is a library class. So as soon as you type it, you can say control space. Now you can import it from Java util. Okay, so array list, and then it's going to be this one. Be careful. We want to say every element in the array list should be a BST node. And the BST node itself is generic. All right, so be careful. Watch out the difference here. So here it's going to be BST node. And that itself is going to be generic. So if you instantiate this one, the E here, to be string, like in the JUnit test, and this E here will be instantiated accordingly to string as well. That means every node is going to store string. Okay? And then that's the return type. And then we have in-order traversal. In order, if you are worried about making typos, you can just copy and paste, the name from the JUnit test. That might be the safest way to go. BST node, that will be the root, the starting point, E, and then the root. And I'll just say return null, just for now. Okay? I want to make sure everything compiles. Oh, BST node has not been imported just yet, right? Got to make sure. Okay? You can go to the end of the BST node, control space, and it's imported from the tests. Okay? All right. The other method, I'm just going to declare that very quickly now so I get rid of all the compilation error. Okay? So that one is about the search. Public, BST node, E, and then search. And then BST node, E, and then starting from some parents or root, and then integer k, right? That one, you can take a look at the solution, okay? I'll just return null, just for now. So now everything compiles. But if I run the test cases, of course, everything fell. That should not be surprising, right? Just double check. And we're going to do one of them, okay? Run as JUnit test. Good, right? So I'm not just going to focus on the in-order traversal, which will be the second test. Let's do that one there, okay? So BST utilities, okay? So there are different ways you can program recursively. You can feel free to show me your solution. I can maybe take a look. Maybe it will just work. I'll just show you one way to do it, okay? In this case, what we can do is we can try to, because we're going to accumulate the list, as we are trying to do the tree traversal. And when we try to accumulate the list should be passed like an argument using call by value, as we learned from 2030. Okay? So the way to do it is like this. Okay? So this is the public method. Public method used by JUnits or any user. Okay? However, internally, you can actually create something called recursive helper method. That's private. Okay? That one there is going to do the trick about recursion. Okay? So we can do private over here. And then let me make it void. Okay? Because I'm going to use the call by value to actually accumulate the list. I don't need to return the list. So void, and then I can simply copy the name over here, and then I will just append helper to it. Okay? So I still need a root, but I'm just going to add one more parameter to it. That one there is going to be the list that I want to create. I want to accumulate, over all the recursive call. Okay, I'm going to copy that and put it here. Okay, let's say that's the order I want to eventually return. Okay, recursive helper method, right? Void, because I can simply pass around that order array list called by value. So that means no new array list is being created. We're just accumulating the same objects. Okay. So what we do is, let's see here. Okay, let's now do something here. There should be only a single list I'm going to create and then pass around. Okay, so I'm going to say, let me just copy this type here. So eventually I want to return some order, initially empty. Array list. By the way, in Java, when you're trying to say call the constructor, you don't have to pass BST node over here. It's going to be figured out by Java anyway. Okay, just something to note. Eventually, I want to return this very same object, return the order. However, before I return it, I want to pass that order to the recursive helper method. That's what I would do. Okay, so I'm just going to say, in order traversal helper right here, and then whatever route I'm being passed over here, I'm just going to pass it. And then the order I just created, I'll put it here. Okay. It is expected that order due to call by value will be modified by the recursive calls. Okay, so far? Okay. Of course, I'm trying to maybe just go a little bit faster, right? Because that's something you may have already done in 2101. Of course, you can reach out to me if you need some extra help on that. Okay. How about recursive helper method? Here, it's going to be very straightforward, right? We want to make sure we don't really include the external nodes in the order, right? It's like because external nodes don't store any meaningful key values, so we want to exclude them. Okay. So here we want to make sure if let me just make a little bit more space. We can say over here, if the route that we are visiting, for example, if we are already, if we are already saying, I want to do in order traversal on this external node, I can skip, nothing to be done. Order can remain the same. But if I'm actually doing in order traversal over here from this particular route, that means I should really recursively do in order traversal here, recursively do it here, and also append this in the middle, right? So that's what the in order traversal will do. Okay. All right. Let's do it. Okay. I'll say if the root dot is internal, right? I'm calling some method from the BST node. Of course, that's something you should really get yourself familiar. If it is the case, I can do something. Otherwise, I can you don't really have to say else part because we can just do nothing. But I'll make it explicit. If the root is not internal, then it must be external, right? This means root dot is external is true. And we simply say an external node will not contributes to the in order traversal 6. Okay, we simply do nothing. The order can keep the same. Okay, keep unchanged. And this branch over here is actually going to actually do the thing, right? And this one here, let's see. Any suggestion? How about that? What should I type? Diego.
How about you call the same method on the left sub?
The helper method?
Yeah.
Yes, recursive helper method. Yes, exactly. We call it recursive helper method because this is where the recursion is going to happen, right? Very good. I agree. By the way, how many times should we call that?
Once on the left subtree, and then you append the current root.
Aha, awesome. Good, good, good. I agree. Okay. Let's be careful here, right? It's simple, task, but it's good to, be careful. I'm going to make a one recursive call right here on the left. Recur on the left. Another one here is going to recur on the right. And you said in the middle, what should we do in the middle? Well, I'll worry about the recursive call a little bit later. In the middle, what should I do?
Append the value of the root.
Append the value, okay. Okay, so now in this case, of course, there's a method from ArrayList called add. You can look up the API for that. By the way, during the programming test, you will be given Java API, right? So, but I would suggest get yourself familiar with the common methods as well, okay? You can save time. Order.add, and just the root, right here. All right? Anybody want to suggest just one line? For the other one, I'm not going to bother you. What should I type? Apparently, you need to pass two things, right? Can I pass the root over here? Go ahead. Root.getLeft, exactly. We're going to recur on the left. Absolutely. Okay. So what we do is root.getLeft. And symmetrically, here we're going to say root.getRight. And then what about the second arguments there? Should we create a new array list for order? Should we? We don't need to, we don't need to, right? Yeah. Just order, right? Call by value, right? By the way, if you don't really know what call by value is, it's okay, but you got to reach out to me, right? Because I would assume you guys know what call by value is. All right, we're going to accumulate the same objects. And of course, I need a semicolon. All right, I believe it is done. So what we'll do is we can now go back, rerun the test. All right, of course, the second test is failing. I haven't implemented it yet. But this one here about in order traversal, that one's passing. Okay. Question about this? Diego.
Are there any Java collection libraries that will be excluded to be used on the...
That's a good question. You know what? Let me answer the question more carefully, maybe once I release the assignment. Sure. Okay, let me confirm that. Okay, yeah. But I can tell you that for your fellow student from last semester, also for 3101, when they implemented graph, they had to use ArrayList. They're allowed to use. They also had to use hash map as well. But that's something you'll get a chance to practice, don't worry, in the assignment, right? More or less it will be similar for this semester, but I'll confirm, okay, a little bit later. All right, so that's about in order traversal. And for the search, there's only one more thing I would like to talk about, and then we're done today. Just up to 5 minutes, okay? I want to talk about conceptually how the searching can be understood, all right? You know searching, how that should be done, right? But now I want to make it a little bit more connected to how the Java code can be understood, right? You can look at the JUnit test case for the second, that one is still failing. You can take a look at that and also implement the search. The solution is there, okay? So what I want to talk about now is about searching here very quickly, okay? And as you can see, we got internal nodes and also external nodes right here, right? So let's say we already set up the tree in the JUnit test, let's say. So now we want to search for the key, right? Let's say we want to search the key for 65 and also 68. Of course, 65, you can see it's there, right? But 68 is actually not there. But we want to see what the difference should be. That's something you want to keep in mind as well when you see the solution. So what we do is, well, you know how the search should really go, right? 44, 65, larger than that, go to the right. 88, 65, less than that. Oh, good, found it. So this tells you that it's a successful search right here, okay? So this is a successful, meaning that an internal nodes is returned. All right? The more interesting case is about unsuccessful search. Okay, that's something I want to tell you. Okay, but we can elaborate about the theory part a little bit more when we talk about insertion deletion when we get back to the classroom next Monday. Let's say this one here is 68, right? Let's try. I got 44 as the root. 68 larger than that, I should go to the right. Yes. And then 68 less than 88, I should go here. 68 larger than 65, I should go to the right. And 68 less than 82, I should go to the left. 68 less than 76, so I go to the left, and then I hit an external node, which is a base case. First of all, this is the node that's going to be returned. You don't really return null when you don't find some key. You always return something. You can think about, we can do instance of check. Sorry, not instance of, I'm going too far, right? You can check to see if the node is either internal or external. If the return node is actually internal, it will be successful search. If the node is, that's return is external, that would be unsuccessful search. Okay? Let's talk about it very quickly. So this will be unsuccessful search. That means external node return. Okay, I want to spend about 2 minutes talking about why returning this external node could be beneficial. Why don't we just return null? And I'll give you a little bit hints here. Let's say we have this particular subtree. Let me call that N1, N2, okay, node 1, node 2. And also node number 3, node number 4, node number 5, node number 6. Apparently, now I'm returning node number 3. Why would it be so useful if I can just return to you the reference to node 3?
You can know the parent. You can know the parent if you have the reference.
Yes, in true, I can know the parent 76, and then?
In case you want to add the missing node.
Add a missing node? There's no missing node here.
The node you're searching for, if it's not in the tree, you can add it.
Yeah, that's true. Yeah, that's pretty good. Yeah. Okay, maybe that's what you meant to say here. Oh, somebody else, sorry. Did I see someone raising their hand? Maybe, oh, sorry, my illusion. Okay, so here, okay, that's exactly right. Okay, let's now see this. If you actually try to do the in-order traversal just for this subtree over here, right, very quickly. Give me 1 minute, and then I'll be done, okay? If you do in-order traversal, you're going to get N1, and also 54, and then N2, and then 65, and 3, 76, and then 80. Oh, sorry. After 76, and then you got N3, followed by N4, 80, and then N5, etc. Right? So now, what we return back was N3. Right? If you look at the in-order traversal, what we said yesterday in the class, what node can I put in between 65 and 76? Any value in between them. So now 68 is exactly one of the possible values. Okay, so N3 key can be replaced by the 68 right here. The reason, which you will see a little bit once more on Monday, when you want to do insertion for binary search tree, usually you will start with a search. If the search for that particular node you want to insert already exists, just replace the node. If the node you want to insert doesn't exist, whatever external node has returned, set it up accordingly. Okay, so that's something we'll see a little bit more. All right, thank you so much. So I think we covered everything. You can see the rest on the site.